Good day everyone. So in this video we will discuss about how to use the i2c bus to control the speed of DC motor. So basically i2c is a communication protocol which is used to interface different sensors with the microcontroller. But in this video I will be using two microcontrollers connecting with each other using a ADC, using your i2c. Right. So actually in this particular video I will be using the same pattern as I have done it with UART based speed control of DC motor. So on the transmitting microcontroller I will be having an ADC, and based on the analog input value of ADC, your PWM of the receiving microcontroller will be changing, and eventually based on that PWM your DC motor speed also will vary. So this is the pattern that I am going to use, so which I have done already with the UART. So the setup is the hardware setup is almost similar. Only thing is, instead of UART communication I am using this i2c. So my transmitting microcontroller will behave like i2c master, while receiving microcontroller will behave like i2c slave. So at any time, as far as i2c bus is concerned, at any time any microcontroller can become a master or can become a slave. Master transmit, master receive, anything it can do. But as of this particular video I will be doing only one version, that is your transmitting microcontroller will be master transmit, and your receiving end microcontroller will be like slave receive. So having said this, let us directly go to the program. So the first program, basically we have to do two programs. So one is for the master, that is transmitting microcontroller, and the other one is for receiving microcontroller. So here in this transmit microcontroller you can see, I have copied the startup.s up to the line number 411, and here this part is the initialization for your code area, and you're declaring the space with a name, and you're declaring that this is code, and it will be written in read-only memory. So these things you declare. Then I am declaring the individual registers with its memory address, so that inside the code I will be using this label rather than using this address. Right. So first I am declaring pin cell 0 as 50. So this is to activate your i2c pins. Right. Basically i2c has two pins, that is serial clock and serial data. So serial clock and serial data is enabled in these two pins. So when you are giving 50 in pin cell 0, what happens is your 6th and 4th bit gets active. So that is specified here. So let us check what is the 6th and 4th pin specified in our pin cell 0 register. 6th and 4th pin. So here 01 specifies P0.3 as serial data, and 4th pin 01, 5th and 4th pin 01, if you specify, P0.2 will be declared as serial clock. So that declaration we are making using these three statements, and here this part is enabling your analog to digital channel. So analog channel in P0.30 by making 100000 in pin cell 1 register. So what does this signify? So pin cell 1, if you are making 10000000, it means that the 28 pin you are making it high. So what does that 28 pin do as far as pin cell 1 is concerned? Let us get into the pin cell 1, and 28 pin, if you are making it high, so 01 means P0.30 is made as AD0.3, that is your analog pin is connected to P0.30. As far as this initialization is concerned, this is based on the hardware, right? So the hardware that I am using is NGX Blue Book, wherein already in the channel P0.30 that is connected with AD0.3, a potentiometer is already connected in the board with a screwdriver. So when screw, not a screwdriver, screw. So when you go for rotating the screw, obviously your analog voltage changes. When analog voltage varies, so there will be a variation in the digital value. So that digital value is going to be transmitted through the I2c to the other microcontroller, and that value will be deciding your pulse width of your PWM. So for doing that, I am initializing this pencil 1. Then coming to this VIC interrupt enable, I am activating this ADC interrupt using this 40000. So let us see what does this 4000 signify. So VIC interrupt enable. So 40000 signifies that 18th bit is high, right? So let us get into the VIC interrupt enable register. So this is your VIC interrupt enable register. 18th pin is AD0. So analog to digital converter 0 is enabled with interrupt. So you are enabling the interrupt of AD0 using by activating this one. So that is done. Then VIC interrupt select, I am making it 0, so that I am declaring that whatever the value interrupt that I have activated will be an normal IRQ, not an FIQ. So if you want FIQ, again in this case, in this VIC interrupt select, it has to be mentioned as 0x40000. Then VIC vector control 0. So in VIC vector control 0, I am moving a value 32. So what does that value 32 signify? So you can see 32 signifies your 5th bit, 4th bit is high, and your 1st bit is high. So 5th bit is the slot enable, and this 4th bit up to the 0th bit specifies the slot number. Okay, so coming back to the VIC vector control register. So this is your VIC vector control register, wherein I will have to enable the slot and specify the slot number. So slot number is given by, you can check it in your interrupt enable register itself. So that happens to be 18 in decimal. When it is getting converted to hexadecimal, it is 1 2, so 12. Right, so 18 when it is converted to hexadecimal, it is 1 2. So obviously when you are making it as 1 2, so the value that you are putting over here will be like this 4th bit will be high, and this one will be high, so it becomes like 32. So that is specified over here. Then VIC vector address 0, I am specifying the address where it has to jump to, that is interrupt service routine where it has to jump to when an ADC interrupt is generated. So as far as when ADC interrupt I am activating, it signifies that when a done bit is set in your analog to digital data register, there will be a done bit, and when the done bit is set, interrupt will be generated, and when an interrupt is generated, it goes into the interrupt service routine, and in the interrupt service routine I will be reading the content of the data register, and I will be transmitting it to the other microcontroller through the I2c. So this is the pattern. And coming to the next one, AD0 interrupt enable register. In AD0 interrupt enable register, I am moving a value 08. So 08 when I move, it means that the 3rd bit I am making it high. So what does that 3rd bit signify in your AD0 interrupt enable register? So 3rd bit, it is making AD interrupt enable 3 active. So completion of a conversion on ADC channel will generate an interrupt. So this I am activating by making this 3rd bit as high in analog to digital converter interrupt enable register. Then AD0 control register. So this initializations we have seen already in detail in the analog to digital converter video, and even in ADC based speed control and UART based speed control. Anyway, I am repeating that again. So here this 250F08 is getting transformed like this. Your 21st bit, which is making your power down mode to go high, it brings your microcontrollers analog to digital converter from power down mode to power up mode. Then I'll have to give the value of clocks. So 19, 18 and 17 I'm specifying 0, 1, 0. So let me show you what does this signify. Actually this signifies the number of bits that you transmit and the clocks 19, 18 and 17. Yeah, 19, 18 and 17. If you are giving 0, 1, 0, your analog to digital converter will use 9 clock per 8 bits. So since my transmission and as far as I2c is concerned, it can communicate with 8 bits only. So I am choosing this 8 bit. So that is convenient for me to transmit the data towards the other microcontroller. Even though your analog to digital converter is capable of having 10 bit ADC, I am reducing it to 8 bit using this initialization. In 19, 18th and 17th bit I am moving 0, 1, 0 respectively. Right. So then I am making the 16th bit high to make your ADC to go in burst mode. Burst mode, obviously you know, when there is a subsequent changes in the value of analog input, automatically the change will be reflected in the digital value. So that is the burst mode. So to do that, as far as any this kind of setup is concerned, burst mode gives you a proper working, because you will when you are changing any parameter, you would expect the change to happen immediately at the other side. So to do that, this will be better. Then in clock division, so here I am specifying 0f. So the value of your clock that is being divided will be of f. So when you reduce this value, the clock divisor will be less, so your frequency will be higher. So as far as your hardware is concerned, when I am having this f, it gives a a smooth transition, or the working of your microcontroller, the transmitting and receiving on the other side happens to be smoother. Then the third bit I am making it high to select the channel. So third channel of AD0 and selecting by making this third bit high. So that is AD0 control register. Then I2c 0 concept register, I am moving a value 40. So this 40, what it does is I am making this I2 enable, right, and the rest of the things are all 0, right. So there are different other bits available, so we'll be using it in the subsequent instructions. So as of this particular statement, I am just enabling the I2c. Then I am moving a value towards your I2c0 SCLL and I20 SCLH. So the clock value lower, clock value higher. So this is moved with the value 8 and 8. So as far as this I2C0 SCLL SCLH is used for deciding your I2C bit frequency. So I2C bit frequency will be based on this formula. So P clock divided by I2C SCLH plus I2C SCLL. So since we have moved 8 and 8 in this case, your value of the I2C bit frequency will be 187500. So assuming that, not assuming, as far as our board is concerned, since the frequency, crystal oscillator frequency is 12 megahertz, generally the peripheral clock frequency will be of 3 megahertz, since the default slashing factor is 4. In case if you vary this slashing factor using the phase lock loop register, then you can make it to 1. Make the slashing factor to 1 and it becomes 12 megahertz. As in this program, I am not doing the changes, so I am keeping it as 3 megahertz only. So since it is 3 megahertz, so 3 into 10 power 6, so that divided by 8 plus 8, so it is 187500 is the frequency at which your I2C is communicating. So that we have transmitted, transferred into the I2C0 SCLL and I2C0 SCLH. So coming to the interrupt service routine, I am subtracting the link register by 4 and moving the content of link register to R6 register. Then I am reading the content of AD0DR. So AD0DR is the data register, analog to digital converter. 0 data register. 3 represents the channel, right? So from there I am reading the content to R4. Then I am I'm moving R1 with the value FF00. So what does this signify? So you should understand, any data register will have this pattern. So this is the pattern of your analog to digital converter data register. 31st bit is done bit, 30th bit is overrun bit, while 15th and to 6th bit, 6th to 15th bit will have the result. So since we have declared or initialized your control register that your ADC will be of 8 bit, so your digital data will be available from 8 to 15. So 6th and 7th bit will be of no use. So the data will, no data will be available in 6th and 7th bit. So these two bits, these two digits, we are making FF and we are storing it in R1 register. This is basically to mask the other bits and extract only the data that we are concerned with. So how do we extract? We are ANDing this R1 register with the content that we have read from the data register. So after ANDing it, so obviously the extracted value will be available in the R7, and then logical shift right R8, R7, #8. So 8 times I am shifting it right. So why should I shift it right? Because the value is available from 8 to 15. So this value, after this you are having 2 zeros. So generally the 8-bit value should be available in your units and tens, right? So if it is available here, these zeros will add to the values of this one and it will give you a wrong data. So to avoid that, we'll have to bring it to the units and tens, right? So to do that, you are doing this LSR R8, R7, #8, and I am moving the value that has been rotated in a memory address 40000. So then this is for our reference, right? Then I am starting this I2C0 concept register. Coming back to I2C0 concept register, I am making this STA bit high, right? So let me show you your I2C0 concept register. So in I2C0 concept register, you can see that your 7th bit is reserved, 6th is I2C enable, then 5th is start flag, 4th is stop flag, SI is I2C interrupt flag, and the 2nd bit is assert acknowledge flag, 0th and 1st bit is reserved again. So as in this instruction, since we are moving to 0, we are starting the I2C. Already we have moved a value I2 enable, right? So you shouldn't be confused, since we already we are moving this 1 and then a 0 over here in I2 enable. Will that be disabling your I2C? No, it doesn't. because I2C0 concept register has a pattern in such a way that when 1 is moved into a concerned bit, that bit will will change to set, while if you are moving a 0 into it, it will not have any effect. So in case if you want to deactivate that, you should use I2C0 con clear register. So whichever the bit that you want to deactivate in the I2C0 concept register, that concerned bit you will have to make it high in the I2C0 con clear register, so that gets cleared. So otherwise you need not worry about the bit which you have activated already. So the one that we have transferred already will be remaining there only, and we are starting the I2C0 I2C by making your start bit. So using this we are starting it. Then I am reading the content from this I2C0 concept register, and I am doing AND with 08. So what is the function of 08? So 08 in the sense I am checking this SI, right? So SI signifies whether your I2C is ready for doing any transaction. So I2C interrupt flag, right? So this particular flag I am checking by ANDing it with R1 and then checking whether the value that I have extracted is the same. So this is for checking the SI bit whether it has gone high. So if it is not, then BNE means branch if not equal. Again and again I will be reading and checking whether your SI bit is gone high. If it has not gone high, it will be rotating here. Once the bit has gone high, then I will be moving a content 28 into I2C0 con clear register. So what does that signify? I2C0 con clear register 28 STAC and SIC. That is your start bit I am clearing, and your interrupt bit also I am clearing. So that is the meaning. So if you want to see the I2C0 con clear register, so this is your I2C0 con clear register. Almost everything, every bits will be similar. Only the change will be in the I2C0 concept register, it will be EAA, here it is EAC, and there it will be SI, here it will be SIC. So the clear signifies that it's a clear bit, and STAC start flag clear bit, and I2C enable there, and this one is I2C enable clear bit. So these things I am doing over here. Then I'm reading the I'm using this I2C0 address, and I'm putting a value 1 into it. So I2C0 address will basically specify the address to which your microcontroller, this particular I2C bus to address to. So here I2C0 address registers format has been shown. Here you can specify any address over here. If you are specifying this 0th bit as high, it means general call. General call means it will be for other microcontrollers which is having the general call as a function. So you can using this particular general call, using the master microcontroller, you can address to different slave microcontrollers which is having this general call. So I am using that over here in the transmitting microcontroller, both in the transmitting microcontroller and the receiving microcontroller. I2C0 address I am making it as 0x01. So next is the I2C0 data register. It's a 8-bit data register. So wherein the content that we have received from your data register, the analog to digital converter data register, will be transferring it into R8 register. You can see R8 register is the one which is available here, which is having the extracted and rotated value. So that value I am moving it into this I2C0 data register. Then I2C0 concept register, I am making it 60. So this 60 signifies again that I will be enabling the I2C enable and starting it. So 6. So enabling and starting the communication, right? So actually this part is to take the control of your I2C. So I2C works in a way like it is available, and your present microcontroller has to go into bus arbitration, and it has to take the control when the I2C is free. So when I2C is doing some other communication with some other master, then this cannot happen. So to do that, your SI bit is being checked over here. Once it has been checked, and when things have been found that it is free for you to communicate, then you start this writing the data into the I2C0 data register and starting the communication. So using this 60. Then again I am reading the content from I2C0 concept register. Again I am checking the SI bit over here, right? So I will be staying here until your SI bit goes high. Once it goes high, then I will make the I2C0 on clear register, that is SI clear bit, right? SI clear bit I will be activating, so your SI bit gets cleared, right? So once it has got cleared, then I will have to stop it. So how to stop it? I will be moving in I2C0 concept register, this I2 enable and stop I will do. So with this your stopping happens, and then I will be clearing the BIC vector address by putting 0 into it, and I will be forcing my microcontroller to go into user mode from IRQ mode. So generally when interrupt happens, your microcontroller goes into IRQ mode. We have to bring back into user mode by doing this. So once that has been done, the reverse of this one will happen. So why I am using this MOV R6, LR is I am saving the content of the link register in R6, so that in case if something has got tampered, the link register has got tampered, that doesn't affect your returning back. So that I am doing here, and then DXLR. So this is your transmitting end program. So let us simulate it once. So I am using this analog to digital converter 0.3. This is our concern, and we'll have to check what is the data that is getting transmitted, right? So I'll start the running of the program. So as of now your AD 0.3 is having 0, so 0 is getting transmitted. Let me change this to 1. So you can see there is a change over here. The same change is getting reflected, 4D and 4D. 4D is getting transmitted in the I2C. Then let me change it to 2. So 9B is getting transmitted. Then I am making it 3. So E8 is getting transmitted in I2C 0 data register. So that is getting transmitted in the I2C. So this is the concern for transmitting and code. Next let us see the receiving end code. Okay, this is your receiving end code. So wherein what we are going to do here is we will be using I2C interrupt and the PWM. So the PWM will be using in single edged mode, and the pulse width of the PWM will be decided by the data that is received from the I2C bus. So as in the previous program, this is declaring the code with the area, the name, and specifying that this is a code, and this available in the read-only memory, and these are the register initialization with the memory address. Then coming to Pincel 0 initialization. So here we'll be initializing two things. One is I2C pins initialization, and the second is the PWM initialization. So both the things are done in the Pincel 0 register itself. So Pincel 0 is specified as 52, which is making 6th bit high, 4th bit high, and this 2 is making this 1st bit high. Let us get into the Pincel 0 register. So Pincel 0 register. So as we have done in the transmitting and program, same SCL0 and the SDA0 is connected with P0.2 and 0.3 respectively by making this 4th bit and 6th bit high, and your PWM1 is connected to P0.0 by making your 1st bit high. So 1st bit, 4th bit, and 6th bit. You can see that 1st bit, 4th bit, and 6th bit. So this 5 indicates that SCL and SDA is activated, and this 1st bit is, but 1st bit signifies that your PWM1 is activated. Then I2C 0 onset register I am making 40. So again this 40 activates your I2 enable, right? I2C enable, I am enabling in this I2C 0 onset register. Then I2C 0 SCLL and SCLH I am making it at 8 and 8. So that basically is the same calculation that we have used in the transmit microcontroller. So in both the cases it should be the same, so that you don't have any variation in the bit frequency, right? The speed at which your data is getting transmitted. So I2 SCLL, SCLL, I2C0 SCLL and I2C0 SCLH is 8 and 8. So 3 megahertz divided by 8 plus 8, so that happens to be 187500. So this again 3 megahertz is obtained from this calculation, assuming your board frequency. It's not assuming, your NGX board is having 12 megahertz crystal oscillator frequency, so 12 divided by 4, that is 3 megahertz. So that initialization you are doing in this case. Then VAC interrupt enable, right? 200. So VAC interrupt enable, you are activating this 9th bit. So let us check what does that 9th bit signify. So in interrupt enable register, 9th bit signifies I2C0 interrupt. Okay, so I2C0 interrupt I am activating. So this is the slot number also. So VAC interrupt select I am making it 0, so that your I2C0 interrupt is normal IRQ, not an FIQ. Then in VAC vector control 0 I am moving a value 29. So 29, as we have seen earlier, this 5th bit is slot enable and 9 is the slot number. So 9 is the slot number. As 9 falls under the value 10, obviously from 0 to 9 hexadecimal and decimal will have the same value, so you can represent the same thing in the control register as such, VAC vector control register as such. Then VAC vector address 0, I am initializing the label IRQ handler. So this specifies that your IRQ handler label is where your interrupt is available. So the memory address of this particular label is getting connected in the VAC vector address 0. Then these initializations are all common with your PWM code. Anyway, let us check it once. PWM PR is a prescaler register where I am moving 0 to so that you are designing your P scalar to 1 microsecond. And PWM MR0 I am making it as 100. So why I am making this 100 is your ADC we have declared it as 8-bit and the communication is happening with 8-bit. The maximum value for 8-bit is FF. So FF plus 1 is 100. So pulse width it shouldn't go up to 100. I mean it will not. Generally when your maximum value is FF, so it will stay at FF only. So obviously the maximum will be limited accordingly, right? It may not go up to 100. Then PWM MR1 I am giving an random value 01. So 01 is the initial value. If you are giving 00 or if you are not initializing also, it's not a issue. And PWM MCR register I am making it 2, so that your reset of your PWM MR0 happens when match happens, right? These things we have seen in the PWM video itself. Let me show that once again. PWM MCR, match control register, PWM MCR. So I am activating this first bit high, so that reset on PWM MR0. The PWM TC will reset if PWM MR0 matches it, right? Then PWM LER, latch enable register. So PWM MR0 and MR1 latch I will have to enable it. So those two bits contribute to the value 3. So PWM, enable PWM match 0 latch and match 1 latch. Then PWM PCR 200. So the PWM enable I am doing in this PWM PCR. So let me show you the PWM PCR. So here PWM PCR I am making this PWM enable in the 9th bit, right? So 9th bit happens to give you your 200. You can see here 9th bit, so 200. PWM PCR. Since we are using single edged, we are not initializing anything over here. So if you want to use double edged only, then you will be selecting for the concerned PWMs. As in this case we are using single edged, we are just doing this PWM enable 1, that is sufficient. Then PWM TCR2 and PWM TCR9 is for resetting your PWM timer and starting your PWM. So that also I will show you once. PWM TCR. Yeah. So counter enable and PWM enable. First you reset the counter, then you enable the counter with the PWM enable. These two things you do. Then i2c0 concept register, you are making it as 0x24. So what does that signify? Start and assert acknowledge. So basically assert acknowledge, if you are making it high, that makes your I2C bus to go into slave mode, right? In the previous transmit code we didn't use this assert acknowledge, but when you are making this assert acknowledge high, it makes your microcontroller to get attached with the I2C as a slave mode. So we are starting it. So already we have enabled it here. Now we are starting it with slave mode. Then next is when interrupt happens, it gets into your interrupt service routine, and I2C0 address I am making it as 01. So 01 makes your microcontroller to get into the general call mode that I have mentioned earlier also. I2c0 address, if you are making the 0th bit high, it uses the general call mode. Otherwise you will specify any specific address over here. So in the master microcontroller, if that particular address is addressed, then this microcontroller will respond to that. So when multiple microcontrollers does have the same general call as high, this general call microcontrollers will respond to that. So as in the case, we are assuming that multiple microcontrollers are being connected through I2c. In case if multiple other sensors are connected, that will also work in the same way. Okay, I2c0, I mean address you have specified, we have specified, and we are reading the content from I2c0 data register, and we are masking the other bits, and we are confined with only the last 8 bits, and we are extracting that into R4 register. Whatever the content that has been obtained in the R4 register, we are transferring it into PWM MR1, so that decides your pulse width. Then I2c0 con clear register, you are moving 08 into it. So I2c0 con clear register, when you are moving 08, so it clears your SI bit. Then VIC vector address, you are flushing it, and PWM. So when you make any changes in the PWM MR1, to make the change of contents to get effective in the output, you need to do the latch again. So that latching is being done here. Then I am stopping the I2c0 conset register by moving 50 into it. So this 50, you can see I2 enable, and I am doing stop. These 2 bits I am making it high. Then I am forcing my microcontroller to go into user mode from the normal IRQ mode. Then I am moving the content from R6 into the link register, and BXLR will return your program counter to the main routine. So this is concerned with your receiving end code. So now let us simulate it once. So in this case, I'll use this I2c peripheral window along with the PWM. Actually PWM is not required. We'll use this logic analyzer, and in the logic analyzer port 0.0, and we will start. So now your value is 0, so you are getting a 0. Let us give some random value. So you can see that the pulse width has increased, that is you are getting pulse width, because initially it was 0, so there is no pulse width. Now I will change it to maybe 7F. So 7F when you are giving, so it's like duty ratio is 50%, and I'll try to make it F0. So the pulse width is maximum. So this is the simulation part, and regarding the hardware, we need to know from which pin you need to connect. So since we are using this NGX blue board, I will be using this P0.2, that is P0A2 as SEL0, and P0_A3 as SDA0. So I need to check in which J's this thing is available. So in J2, P0A2 is there, that is the 6th pin, and P0A3, that is your 10th pin in J2, and the PWM is available in P0_A0. So that P0_A0 is available in the 3rd pin of J2, and I'll be getting the PWM from third pin and second pin. From here I can go for connecting the chopper, and from chopper DC motor connection can be made. So this is the way in which you can do the connection, while the 6th pin and 10th pin of this microcontroller should be connected to the 6th pin and 10th pin of your transmitting microcontroller for the connection, I2c bus connection to happen. Let us see the hardware working. So this is the LPC 2148 where we have dumped the transmit program, and this is the one where we have dumped the receive program. So here from the J2 junction, we are taking this pins 6th and 10th pin, while 6th is your clock, serial clock, and 10th is your data, serial data. So this 2 pins we are connecting it to the second microcontroller, that is the receive microcontroller, wherein in the second microcontroller we are using this J2's second and third pin, which will be providing the PWM. So based on the ADC signal, your PWM will be, the pulse width of the PWM will be decided, and that is being fed into the optocoupler, and from optocoupler it is being given to the chopper, and based on the chopper, based on the PWM, the chopper will be controlling the speed, controlling the voltage that is fed towards the DC motor. So again, voltage, based on the voltage, the DC motor speed varies. Okay, so we have dumped the transmit code in this board and the receive code in this board, and this is the J2 series of pins, from where 6th pin I have connected to the 6th pin of the second microcontroller, and the 10th pin to the 10th pin of the microcontroller, while you can see here the second pin is the ground, and the third pin is the PWM. So that we have given to the optocoupler, and from the optocoupler we have given the connection towards the gate and source, and you can see across the across your load, instead of load resistance we have connected the DC motor, and it is revolving. So you can see from here now this particular DSO shows the optocoupler's output, while this DSO shows the output across the chopper load. So now I'll try to vary the potentiometer for ADC to show the variations in the optocoupler and load and the speed of DC motor. So now I am increasing the ADC value. So you can see the pulse width getting increased. So the same is replicated over here, and the speed is increased. So now I'll try to reduce. So now I am reducing. You can see that motor has reduced its speed. So the control is happening from this board to, the transmitter board to the receiver board. Thank you.